Hey everyone, welcome back to the channel. In this masterclass, we are doing a complete, from the ground up deep dive into design a news feed system. By the end of this video, you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. A single post from a celebrity. 130 million followers. 200 milliseconds to deliver it. This is the core tension in news feed design, and every architectural decision you make lives inside that constraint. We are going to build the mental model that lets you reason about it from first principles. A news feed is a personalized, ordered stream of content sourced from the accounts a user follows. The naive implementation is a single SQL query: select posts from followed authors, order by time, limit 50. That works fine for thousands of users. It falls apart completely at hundreds of millions, and understanding exactly why is the first step to designing something that survives. 500 million tweets per day multiplied by an average of 200 followers each produces 100 billion fan-out operations every single day. A single celebrity post can alone trigger 100 million writes. At the same time, 300,000 feed reads happen every second at peak. These two numbers are the source of every hard trade-off in this design. Quick pause: if this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. Write amplification means a single post fans out into an individual write operations proportional to the author's follower count. Read amplification inverts that a single feed request must aggregate posts from every account the reader follows. Every architectural strategy in this space is trading one form of amplification for the other. The right answer depends on your read-to-write ratio and how skewed your follower distribution is. This is the query that every engineer writes first. Fetch the list of followed user IDs, then run a large in-clause query ordered by time. The problems compound quickly. The in list can hold thousands of IDs, no index efficiently covers a multi-author time-ordered scan, and this entire computation runs fresh on every feed load 300,000 times per second at peak. Latency grows linearly with the number of accounts a user follows. Before choosing a strategy, nail down the requirements. Feed reads outnumber writes by roughly 50 to 1, which already suggests pre-computation pays off. Users tolerate a few seconds of lag before a new post appears. Strong consistency is not required. The hardest constraint is the skewed follower graph. The same strategy cannot be applied uniformly to a user with 200 followers and a celebrity with 100 million. Every news feed system is built on a shared vocabulary. Get these terms wrong in a design interview or in a team discussion, and the rest of the conversation breaks down. Let us lock in the definitions before touching a single architectural decision. A post is the atomic unit of content: a tweet, a photo, a like event. It always carries an ID, an author reference, and a timestamp. The feed is the ordered collection of posts surfaced to a specific user. The word to hold on to is personalized. To users who follow different people see fundamentally different feeds. The follower graph is a directed graph. An edge from A to C means A follows C, but C does not necessarily follow a back. This asymmetry is what makes celebrity accounts, with hundreds of millions of followers, a special architectural challenge. Every fan-out decision you make is a function of this graph's shape. Fan-out is the core operational challenge of any feed system. When a user publishes a post, that single event must be delivered to every follower. The fan-out factor, the follower count, is the multiplier on every write. For ordinary users, this is manageable. For celebrities, it becomes the central architectural problem the rest of this course is designed to solve. The feed inbox is a per-user data structure, typically a Redis sorted set that holds the pre-computed sequence of post IDs for that user. When the user opens the app, you read their inbox directly rather than querying from scratch. But the inbox stores IDs, not full content. Hydration is the separate step where you resolve those IDs into renderable post objects, and it has its own latency and caching profile. A ranking signal is any measurable feature that a scoring formula or ML model uses to decide where a post lands in the feed. Recency is the simplest signal, just sort by timestamp. Relevance ranked feeds weigh dozens of signals and may deliberately surface a 3-day-old post over a 10-second-old one. Twitter's toggle between latest and algorithmic mode is the clearest real-world illustration of this trade-off. Fanout on write pushes a new post into every follower's inbox at the moment of publication. Reads become a simple inbox lookup. Fanout on read does the opposite. Publication is cheap, but every read triggers a merge across all followed accounts. Both strategies are used in production. The right choice depends on the distribution of follower counts and read-to-write ratios in your specific system. Let's trace exactly what happens from the moment a user hits post to the moment a follower sees that post in their feed. We'll go step by step, then examine the data structures and trade-offs in detail. The pipeline has 6 steps, but the critical design decision lives in step 2. Fanout is asynchronous. The post service publishes an event to Kafka and returns success to the user immediately. The heavy lifting, potentially tens of thousands of Redis writes, happens in the background, completely invisible to the poster. The post service handles 2 responsibilities: persisting the post to the database and publishing a single event to the Kafka topic. Fanout workers form a consumer group. You scale them independently by adding more instances. Each worker fetches the follower list once and then fires a Redis write per follower. When user B opens the app, their feed is already waiting, a single Redis read, no scatter-gather required. A Redis sorted set is the right structure here because it keeps members ordered by score at all times with O, log n, writes and reads. Using the timestamp as the score gives chronological ordering for free. Switching to a computed relevance score requires no structural change, just a different number in the Z call, which is why this structure buys you ranking flexibility later. Without a cap, inbox size grows without bound, and RAM costs spiral out of control. The standard approach is to trim immediately after each write using range birang, which removes the lowest scored members. A cap of around 800 entries is typical. It covers far more history than users actually scroll through, while keeping memory usage deterministic and per-user latency consistent. The appeal of fanout on write is that it fully decouples write complexity from read complexity. Every follower's inbox is pre-computed, so the read path is trivially simple. Social platforms typically see read-to-write ratios of 10 to 1 or higher, meaning this trade-off, expensive writes in exchange for cheap reads, pays off across the vast majority of requests. In an interview, stopping at the advantages will cost you the offer. Write amplification is a genuine operational burden at scale, and the celebrity problem is severe enough that most production systems handle high follower accounts with a completely different strategy, which we will cover in the next section. Stale data from edits is especially tricky because there is no efficient way to update millions of already distributed inbox entries consistently. The celebrity problem is the question that separates junior candidates from senior architects in system design interviews. We are going to make it brutally concrete, walk through every mitigation strategy production systems actually use, and then look at real Java code that implements them. Elon Musk posts a tweet and has 130 million followers. At 100,000 Redis writes per second, which is fast, your fanout workers need 22 minutes to deliver that single post. And celebrities don't post at quiet times, they post when news breaks, exactly when your platform is already under maximum load. You don't have one celebrity, you have thousands, all spiking together. The failure cascade is worth tracing carefully. A celebrity post arrives on a Kafka partition. That partition becomes a bottleneck because its fanout job dwarfs all others. The fanout worker pool hammers Redis with 130 million individual sorted set writes, saturating write throughput. Normal user fanouts queue behind it and stall. The hotkey problem is not just about one account, it poisons the entire pipeline. Notice the word mitigate. There is no perfect solution, only conscious trade-offs. Skipping inactive users alone can cut your write volume by 40 to 60% on most platforms. Routing celebrity posts to a dedicated lower priority pipeline protects the critical path for regular users. The hybrid model, fanout on write for normal users, fanout on read for celebrities, is what the industry converged on, and it gets its own dedicated section. Batching Redis writes and using priority queues are mechanical optimizations that compound the gains. The Kafka listener runs with 10 parallel consumer threads. The very first decision after consuming a post event is checking follower count, a cheap metadata call. If the author exceeds the celebrity threshold of 1 million followers, the post is immediately routed to the celebrity queue and the method returns. No Redis writes happen for that post at this stage. Only normal users proceed to the full fanout path. Followers are fetched in pages of 1,000 to avoid loading millions of IDs into memory at once. Each page is then filtered through the activity check. Any follower who hasn't been active in the last 30 days is dropped before a single Redis write is issued. If they return to the platform later, a different code path reconstructs their feed on demand. This is strategy 1 in action, cutting write volume before it reaches the database layer. Instead of issuing one Redis command per follower, all ZDDs and trims for a batch of 1,000 followers are packed into a single pipeline call. One network round trip replaces 1,000. Immediately after each ZD, a range BRM trims the sorted set to 800 entries, bounding the memory footprint of every user inbox. This is strategy 4, pipeline batching, combined with inbox size capping, which prevents unbounded Redis memory growth. The celebrity problem forces you to make explicit trade-offs rather than pretend you can satisfy every constraint simultaneously. The inactive user filter and pipeline batching are low-hanging fruit you implement regardless. The celebrity threshold and priority queues protect normal users from being starved. And the hybrid model, combining fanout on write with fanout on read, is the architectural decision the next section is dedicated to explaining in full. Fanout on read is the polar opposite of the push model. When a user posts, exactly one record is written to the posts table, no queues, no workers, no inbox updates. Every bit of aggregation work is shifted to the moment a reader asks for their feed. Understanding this trade-off is central to choosing the right architecture. When user B requests their feed, the feed service first asks the graph service for the full list of accounts B follows, say 300 users. It then fires parallel reads for each followed user's recent posts. All those small sorted lists flow into a KV merge sort, then through a ranking step, and finally the top 50 posts are returned. Each step is deliberate, parallelism hides latency, and the merge keeps memory bounded. The naive implementation concatenates every post from every followed user and runs a full sort. For 300 followed users each contributing 50 posts, that is 15,000 comparisons on every single read. At scale, that CPU cost compounds into a capacity crisis. The correct tool is a min-heap merge, which only tracks one pointer per followed user and delivers O(n log k) complexity, roughly 400 operations to produce 50 output posts from 300 sources. The min-heap holds exactly k elements, one per followed user, each pointing to that user's most recent unprocessed post. Extracting the heap minimum always yields the globally most recent post across all authors. After extraction, the pointer for that author advances to their next post, which is then reinserted into the heap. This loop runs until n output posts are collected. The heap size never exceeds k, keeping memory predictable regardless of total post volume. The build feed entry point is intentionally thin. It delegates to parallel fetch and then to the merge. In fetch posts in parallel, each followed user's post query is wrapped in a completable future so all 300 I/O calls fly concurrently. To resilience details matter here. A 200 millisecond timeout prevents a single slow shard from stalling the entire feed, and the exceptionally handler degrades gracefully by returning an empty list for any failed author rather than failing the whole request. The quemerge method seeds a max heap with the first post from every author, then runs the extraction loop. Each iteration polls the globally newest post, appends it to the result list, advances that author's pointer via the pointers map, and conditionally inserts the author's next post back into the heap. The loop terminates as soon as the output list reaches feed size, so the algorithm never processes more posts than strictly needed, a critical optimization when followed user counts are large. Fanout on read has an enviable write path, but its read cost grows with the size of a user's following list. For a user following 50 people, it is negligible. For a user following 50,000 influencers, the parallel fetch and merge become expensive on every single request. This is why production systems like Twitter converge on a hybrid strategy: fan-out on write for ordinary accounts and fan-out on read for high-follower celebrities, combining the best of both models. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.